Hello everyone, my name is Mizanoor Rahman. I am a PhD student at Conversely. The topic of my today's presentation is performance evaluation of genetic algorithm and particle sum optimization in off-site construction scheduling. The outline of my presentation is introduction, literature review, methodology, implementation, and conclusion. Introduction: Canada needs to build 5.8 million homes by 2030, which is very difficult to adapt using traditional construction approach. Therefore, construction industry needs some innovative technique. In this aspect, offsite construction can be one of the potential solutions because it reduces energy, waste, time, cost, and it improves the productivity, safety, and quality. So what is the offsite construction process? The offsite construction process mainly comprises three phases. The first phase is manufacturing, and that can be panelized and modular. The second phase is transportation. That means when the components of a building are fabricated in a factory, then it transferred to the site for assembly. So our study mainly focus on the manufacturing process. So what are the manufacturing process? Let me explain it with a typical example where the four workstation involved. So first workstation is the framing workstation where the framing component of the wall is prepared. Then the second workstation is the seating. The station where the seating material like plywood is placed on the wall frame. Then the nailing workstation where the seating material sits with the wall frame. And if there is a door and window, the panel goes to door and window installation station. And after that, it goes to wall magazine station, which is basically a storage area. And if there is no door and window, the panel directly moves to the wall magazine, and later on it transferred to the site for assembly. So the question is how much time to need to complete a project and whether we can optimize it, how much we can optimize it, and which algorithm can be better for optimization, and what are the production sequence which it should adopt. Therefore, the objective of this study is to determine the best algorithm for optimize the production schedule in terms of project completion time among GA and PSO. Literature review in this aspect, several research are used, single algorithm and multiple algorithm. However, there is a lack of study that compare the performance between GA and PSO for optimizing the offsite construction schedule in terms of project completion time. Methodology. The methodology involves mainly three steps. So step one is data analysis. Step two is developing optimization model, and step three is the case study. Data analysis. The first step of the data analysis is to determine the productivity of each panel at each workstation using historical data. The second step is develop histogram to identify the optimistic, most likely, and pessimistic productivity at each workstation. And the third step is calculate weighted average productivity at each workstation using this formula. Then the next step is optimization model. So the objective of our optimization model is to minimize the project completion time, and there is the variable. The wall panel production sequence is the variable, and there is a two constraints. Number one is the sequence of workstation. That means the sequence of workstation cannot be changed. And the second constant is a particular workstation at a time cannot work on multiple wall panels. Then we develop the GA and PSO model. So the GA model, at the very beginning, we have recorded our process time for each wall panel in Excel sheet, and then define the number of workstation, define the GA parameter, and randomly create initial population, and find out the fitness value of each population. Then from there we select the tournament selection process to determine the population. Then we carry out the crossover. Here we have adopt partially mapped crossover process. Then we use the mutation. Here we have adopted the swapping mutation process. Then create a offspring population. And finally, if the iteration is reached the maximum number of generations, it provides the optimum value. If not, then it go to the next generation and repeat the process. And similarly for PSO, at the very beginning we define the initial number of particles, calculate the fitness value for each particle, then find the local waste and global waste from the position. If the iteration is reached to the maximum, then it terminate the process and provide the optimum value. If not, then this go to the next generation, or we have update the velocity of the particle using this formula, where the new velocity is the sum of three components: inertial component, cognitive component, and social component. Implementation, our proposed method we have implemented in a real time, like there is steel oil production factory in Edmonton, and they have a three workstation such as assembly station, framing workstation, and sheeting workstation. And then from the factory data, we analyze the data and develop a histogram to determine the optimistic, most likely, and pessimistic productivity for each workstation. For example, assembly workstation, we find optimistic, most likely, and pessimistic productivity is 0.16, 1.15, and 3.19 square feet per minute respectively. Similarly, for framing and sheeting workstation, we determine the productivity value. Then we have randomly chosen 50 wall panel and run GA and PSO on this 50 wall panel. From here, you can see the GA provide the minimum span is around 2,194 minutes, and PSO it can reduce the completion time to 2,226 minutes. That means GA is provide better result than PSO in terms of minimizing the make span. Then we have considered 13 sets of 13 projects. For example, the first project we 10 all panel, and the last project we consider 160 all panel. And we run both algorithms, and we find that the make span using GA is relatively lower than PSO. For example, 160 all panel, and the make span is 6.12 minutes using GA, and 6.22 minutes using PSO. After that, we compare the runtime also for both algorithms, and we find that the runtime for GA is relatively higher than PSO. For example, for 160 all panel, the runtime using GA is 11.97 seconds and 6 seconds for PSO. Conclusion, the proposed method is employed the GA and PSO to optimize the offset construction schedule, and we have implemented it on a light gauge steel wall panel production factory in Edmonton, Canada. The results reveal that GA provide better result than PSO for minimizing the PSO. However, the PSO generates results relatively faster than GA. There is some limitation because we compare only two algorithms, GA and PSO, and however we have intention to include more algorithms like simulated annealing, ant colony, and traverse algorithm with this GA and PSO to find out a better algorithm among these 5 algorithms. And thank you.